In the beginning, there was no sky, no stars, no matter, and no distance to cross. Time itself had not yet unfolded. Then, within the first instant, the Planck time, around 10 to the power of minus 43 seconds after the Big Bang, the universe existed as a sea of unimaginable density and heat. Physics as we know it falters there, where gravity and quantum mechanics collide into a single unresolved truth. Yet, from that opacity, space began to stretch, not gently, but in an overwhelming surge that reshaped the scale of reality itself. This moment is known as cosmic inflation, an idea proposed in 1980 by the physicist Alan Guth. It describes a fleeting period when the universe expanded exponentially faster than light could travel, growing from subatomic size to something large enough to contain the seeds of all future galaxies. At first glance, this sounds impossible. Einstein's theory of relativity forbids anything from moving through space faster than light, but inflation does not break that law. Instead, it expands space itself. Galaxies and atoms are carried apart not by motion, but by the swelling fabric of the cosmos. Nothing outruns light locally, rather. The arena in which light moves grows beneath it. During those first fractions of a second, quantum fluctuations, the subtle tremors of the vacuum, were stretched to cosmic scales. Tiny differences in density, smaller than an atom, became the blueprints of future galaxies, clusters, and the web-like structure of the cosmos. Where one region contained slightly more energy than another, gravity would later pull matter together to form stars and planets. These fluctuations were not random chaos, but the fingerprint of quantum mechanics engraved on the newborn universe. As inflation ended, the rapid stretching of space slowed, releasing a storm of energy that filled the universe with radiation and particles. This event, called reheating, created the matter that would eventually build every atom in existence. The universe entered a hot, dense state, the phase we usually call the Big Bang. From this point forward, the cosmos continued to expand, but at a gentler pace, allowing light to travel, matter to cool, and structure to emerge. The story of creation had entered its visible chapter. Evidence for this ancient inflation is preserved in the cosmic microwave background, the faint afterglow left from when the universe was only about 380,000 years old. Observations by the WMAP and Planck satellites reveal tiny temperature variations across the sky, mere millionths of a degree, yet precisely matching the patterns predicted by inflation. These small anisotropies are not imperfections but the very imprints of the quantum fluctuations stretched by that early burst. Each cold and warm patch represents a future cosmic continent, a place where gravity would sculpt galaxies out of the early fog. Even today, the expansion that began then continues, although far slower than during inflation. Space is still stretching, galaxies are still drifting apart, and the universe has never ceased to grow. The cosmic story, written in energy and light, began with a question: how could something come from nothing and expand faster than light without violating nature's laws? Inflation answered with elegance, not by breaking the rules of physics, but by revealing their deeper geometry. And so, in those first unimaginable moments, the universe became vast before it became bright. The speed of light remained unchallenged, yet the stage on which light travels swelled beyond any boundary. The echo of that ancient surge endures in every direction, whispering from the microwave background like a fossil of eternity. It reminds us that once, for the briefest flicker of time, the universe was young, wild, and limitless, a space that expanded faster than light itself. As we look across billions of years to that primordial dawn, a single question lingers like the faint hum of the cosmos. If the universe once grew faster than light, could it happen again? And forever? In the shadow of the first cosmic second, the newborn universe pulsed with raw energy, hotter than anything we can imagine. The matter that would one day form stars, planets, and life was still a sea of particles, colliding, annihilating, and reappearing in a frenzy of creation. Photons scattered freely. Unable to travel far before meeting electrons, their paths tangled in the dense fog of an opaque cosmos. Time itself was no more than a gentle murmur of unfolding events, and yet, within that chaos, the architecture of the universe had already been decided. Inflation had ended, but its consequences stretched endlessly forward. The universe was uniform on the largest scales, smooth as an ocean at rest, yet not perfectly so. Those minute quantum ripples left behind were enough to break the symmetry, ensuring that gravity would one day have something to work with. If space had been perfectly even, no galaxies could have formed, no stars would ever have burned, and the universe would have remained a silent haze of hydrogen. Instead, the tiniest variations in density became the scaffolding of all future structure. It was a universe delicately tuned between chaos and order, written by quantum chance and cosmic geometry. As the universe expanded, it cooled, and energy transformed into matter, quarks bound into protons and neutrons. Within minutes, these particles combined into simple atomic nuclei, mostly hydrogen and helium. This brief window, called primordial nucleosynthesis, set the chemical pattern for everything that followed. No heavier elements could yet form, for the cosmos was still too hot and too diffuse. The heavy atoms that build life, the carbon and oxygen and iron within us, would come billions of years later, forged in the hearts of stars that had not yet ignited. About 380,000 years after inflation, the universe reached a temperature where electrons could finally settle into orbits around nuclei, forming neutral atoms. Light, once trapped by endless scattering, was at last free to travel across space. That light still exists today as the cosmic microwave background, a fossil glow that fills every direction of the sky. It is a silent witness to a universe newly transparent, its photons stretching across time as space expands, their wavelengths now stretched into the microwave range. To observe this radiation is to see the first visible moment of the cosmos. This image, captured by instruments like the Planck satellite, reveals a sky mottled with patterns no wider than a handprint at arm's length. Those patterns are relics of the fluctuations that inflation magnified, the very seeds from which every galaxy was born. They tell us that the laws of physics in that early moment were astonishingly simple and consistent. The same physical constants that govern atoms on Earth appear to have shaped the birth of everything. Such harmony across scales hints that the universe was once not only smaller, but also more deeply unified. Physicists study this balance between simplicity and complexity as a key to understanding the ultimate laws of nature. Inflation is not merely a story about expansion, it is about symmetry breaking, about how a uniform field gave rise to the diversity we see today. As the universe cooled, forces that were once merged began to separate. Gravity, electromagnetism, and the nuclear forces each took on their distinct roles. Every atom, star, and planet is a remnant of that cosmic differentiation. When we trace back the expansion, the evidence aligns, galaxies move apart, the cosmic background cools with time, and distant light shifts to longer wavelengths. Each observation reinforces the same conclusion, that the universe once passed through an era of extraordinary inflation. What remains unclear is what triggered it, or what caused it to stop. The mechanism behind inflation lies deep within the unknown realm where quantum physics meets gravity, a place where even our most precise theories are silent. Yet, through observation and mathematics, humanity has pieced together this ancient narrative, turning faint radiation into a map of origins. Inflation transformed the entire cosmos in less than a trillionth of a second, leaving behind not only galaxies but the very rules that would govern their behavior. It was an event so complete that everything we see, from the spiral arms of the Milky Way to the flicker of starlight, can be traced back to its silent surge. Still, the question remains open, echoing through every observation and equation. Was this expansion a singular event, or a glimpse into a deeper cycle written into the fabric of reality itself? Long after the first great surge of inflation, the universe entered a quieter rhythm of expansion. Space continued to stretch, though no longer at the furious pace that once outran light itself. As billions of years unfolded, this slower expansion became the backdrop for everything that followed the formation of galaxies, stars, planets, and the chemical story of life. Yet, the faint echo of that early, faster-than-light growth never vanished. It remains woven into the very geometry of space, influencing how the cosmos evolves even today. To grasp the meaning of that inflationary moment, we must understand how space itself behaves. Unlike a substance or a medium, it has no edges, no texture, no motion of its own. When cosmologists say space expands, they mean that the distance between stationary points increases with time. Galaxies are not flying through a pre-existing void. Instead, the void itself is swelling, carrying them apart like dots drawn on an inflating balloon. In this sense, inflation did not push matter outward into emptiness. It created more space, everywhere, at once. The speed of light was never broken, because no object traveled through space faster than light. Rather, it was the measurement of space that changed, stretching distances beyond what light could traverse. This expansion was not merely physical, it was also informational. Inflation wiped away any irregularities that might have existed before it began, leaving the universe nearly uniform across immense scales. This explains why the cosmic microwave background looks the same in every direction. Light arriving from opposite sides of the sky has traveled for billions of years, yet it began from regions that could never have communicated unless inflation had first expanded them from a common origin. It is one of the great triumphs of modern cosmology that this once puzzling uniformity can be understood as the natural result of exponential expansion. As inflation ended, it did not leave a perfect void behind. The quantum fluctuations embedded in its energy field provided the texture upon which gravity would later work. These tiny variations, 1 part in 100,000, are the reason that matter did not remain evenly spread. Over time, gravity amplified them, pulling denser regions together and leaving empty voids between. Without those infinitesimal differences, the universe would have remained smooth and silent. Every galaxy, every cluster, every chain of stars owes its existence to that delicate imbalance written by quantum chance during inflation. Observations have confirmed this story with extraordinary precision. Measurements from the Planck mission show a universe whose large-scale geometry is flat, just as inflation predicts. The slight irregularities in the cosmic microwave background match the statistical patterns expected from quantum fluctuations stretched by rapid expansion. It is as though the universe itself still carries the fingerprints of that first moment, etched into its background radiation. Each photon of that faint glow has traveled for nearly 14 billion years, crossing a cosmos still shaped by the rules established in its infancy. Yet, mysteries remain. What caused inflation to start? What made it stop? These are not small questions, for they touch the boundaries of known physics. Some theories propose that inflation began as a phase transition in a high-energy field, much like steam condensing into water. Others imagine it as the decay of a false vacuum, a temporary state of space that released its energy as expansion. But these remain hypotheses, awaiting the unifying framework of quantum gravity that could describe them completely. Until then, we can only trace the evidence left behind and marvel at how deeply it agrees with what we observe. The early universe, once smaller than an atom, has grown into a cosmos more than 90 billion light-years across, in observable size. All of this began in less than a heartbeat of cosmic time. That is the true power of inflation, not just that it happened, but that its effects are still unfolding around us. Every expanding galaxy, every redshifted beam of starlight, is a quiet continuation of that first expansion faster than light. As we reach the end of this first chapter, we are left with a thought that bridges the birth of time and the farthest reaches of space. If the universe once expanded faster than light and still carries that momentum within its structure, then perhaps its destiny too lies written in that same unstoppable motion. For in the vast silence between galaxies, we may already be witnessing the echo of that eternal beginning. A universe still unfolding, forever stretching, forever remembering the moment when expansion first outran light itself. For much of the 20th century, astronomers believed the universe was slowing down. The reasoning seemed certain. If gravity pulls everything together, then over billions of years, the cosmic expansion born from the Big Bang must gradually weaken. Galaxies would continue to drift apart, but their motion would slow, perhaps even halt in some far future. That was the picture scientists expected, a universe coasting towards stillness. Yet, in the closing years of the 1990s, the cosmos revealed a different truth. Space was not calming, it was speeding up. The revelation began with faint explosions in distant galaxies. These were Type Ia supernovae, the violent deaths of white dwarf stars that reached a critical mass and detonated with extraordinary brightness. Because these events shine with nearly uniform luminosity, they act as cosmic lighthouses, By comparing how bright they appear from Earth to how bright they should be, astronomers can measure their distances across billions of light years. The idea was simple, but powerful. Map the expansion of the universe by watching how fast these supernovae recede. Two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, undertook this mission. They expected to confirm a slowing expansion, the natural result of gravity's long pull. Instead, what they found shook cosmology to its core. Distant supernovae were dimmer than expected, meaning they were farther away than the standard models predicted. The only explanation was that the universe's expansion had accelerated over time. The implication was staggering. Something unseen, some invisible pressure, was pushing galaxies apart, faster and faster. It was not matter, for matter attracts. It was not radiation, which loses strength as space expands. Whatever this force was, worked in the opposite direction of gravity. To describe it, scientists revived a nearly forgotten concept, the cosmological constant, denoted by the Greek letter lambda, first introduced by Albert Einstein in 1917. Einstein had originally added it to his equations of general relativity to balance gravity and keep the universe static. But when observations showed that the universe was actually expanding, he called it his greatest blunder. Now, decades later, it returned as the most plausible explanation. This mysterious energy came to be called dark energy. Though its name sounds exotic, it simply represents the energy of empty space itself, a property of the vacuum that drives expansion. According to current measurements, it makes up about 68% of the total energy content of the universe, while dark matter contributes roughly 27% and ordinary matter only about 5%. That means nearly everything in the cosmos is made of things we cannot see directly. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery, which transformed our understanding of the universe. What had once seemed like a slow, predictable unwinding of the Big Bang was revealed to be an ongoing acceleration powered by a form of energy we barely comprehend. The expansion of the universe is not coasting to a stop, it is racing forward, with no sign of slowing. The evidence for dark energy continues to grow. Observations of the cosmic microwave background by the Planck mission, combined with large-scale galaxy surveys, show that the geometry of the universe is flat, consistent with a cosmological constant driving its expansion. Baryon, acoustic oscillations, subtle patterns in the distribution of galaxies also confirm this accelerated growth. Together, they outline a universe dominated by a quiet but relentless force, one that resists gravity and reshapes the destiny of everything within it. The discovery raised profound questions. What is the true nature of dark energy? Is it constant through time, or does it evolve? If it remains unchanged, the cosmos will continue expanding forever, its galaxies drifting apart into isolation. If it grows stronger, the acceleration could tear apart even-bound systems, a future known as the Big Rip. Either way, the discovery overturned our most basic assumptions about how the universe works. For now, scientists describe dark energy mathematically, but its physical essence remains elusive. It might be the energy of the vacuum predicted by quantum field theory, or it could arise from some yet undiscovered field that permeates space. Whatever its source, it acts as a cosmic engine, accelerating the fabric of the universe itself. And so, the story of the cosmos shifted from one of deceleration to one of eternal motion. Where astronomers once saw a universe governed by gravity alone, they now see a vast ocean driven by an unseen current. Each galaxy, each cluster, each beam of light is carried along by this expanding tide. As we look deeper into space, we are also looking back in time, seeing galaxies as they were billions of years ago. The farther we look, the faster those galaxies seem to recede, their light stretched into longer wavelengths by expansion. Beyond a certain distance, they move away faster than light itself, not through motion, but because the space between us and them grows too quickly for light to cross. It is a limit not of speed, but of space-time itself, and it sets the stage for a new horizon, a cosmic boundary that defines what we can see, what will forever remain beyond reach. The realization that the universe is accelerating rewrote the final act of cosmic history. For generations, scientists imagined three possibilities for the universe's fate. In the first, gravity would triumph, pulling everything back together in a fiery collapse called the Big Crunch. In the second, expansion would continue forever, but gradually slow, approaching stillness as the pull of gravity weakened. In the third, a perfect balance between expansion and contraction would hold the cosmos in delicate equilibrium. The discovery of dark energy shattered all three expectations. The universe was not slowing, not balancing, but speeding up without end. In this new picture, every galaxy is like a ship carried on an invisible current, a current that strengthens as space expands. Gravity holds small regions together, galaxies, clusters, and local groups. But beyond those bounds, dark energy dominates. Its influence grows with distance, meaning that the farther apart two galaxies are, the faster they recede from one another. This relationship, first described by Edwin Hubble in 1929, is now known as Hubble's law. It expresses how recessional velocity increases with distance, an effect that becomes extreme at cosmic scales. Yet, Hubble's law tells only part of the story. What the supernova observations of the 1990s revealed is that this velocity is not constant. The Hubble constant itself changes over time as dark energy takes control. The fabric of space-time is no longer merely stretching, it is accelerating its stretch. The galaxies we see today will one day vanish from view, their light stretched beyond any detectable wavelength. In the distant future, only the galaxies gravitationally bound to our own will remain visible, adrift in a vast and empty dark. Astronomers describe the current model of the universe with four simple letters: WALCDM, short for lambda cold dark matter. The Greek letter lambda represents the cosmological constant dark energy. Cold dark matter accounts for the invisible gravitational glue that holds galaxies together. This model has withstood decades of observational testing and explains nearly every major feature of the cosmos: its structure, its age, and its accelerating expansion. It is not a guess, but the most successful cosmological framework ever constructed. Still, the simplicity of LCDM conceals profound mysteries. The nature of both dark energy and dark matter remains unknown. Together they account for 95% of the universe, yet they have never been directly detected. Physicists can measure their effects with exquisite precision, but the underlying cause remains hidden. Some theories suggest that dark energy might be an inherent property of space, the energy of the vacuum predicted by quantum field theory. But if this is true, the calculations of vacuum energy overshoot the observed value by an almost inconceivable factor, about 10 to the power of 120. It is one of the greatest unsolved problems in physics, a discrepancy so vast that it hints at a deeper principle still undiscovered. The idea that empty space has energy may seem abstract, but its effects are real and measurable. As space expands, the amount of dark energy does not dilute like matter or radiation. It remains constant per unit volume. That means that as the universe grows, there is more of this energy overall, driving further expansion. It is a feedback without end, a self-sustaining mechanism that ensures the universe can never stop growing. Imagine the universe as a rubber sheet being stretched from all directions. The more it stretches, the more new rubber appears between the edges, pushing them apart even faster. This metaphor captures the essence of cosmic acceleration, an expansion that feeds itself, powered by the very fabric of reality. It is not a force acting on objects, but an intrinsic property of space-time, woven into the geometry of the cosmos. The realization that the universe will not slow down but accelerate forever transformed cosmology from a story of return to one of infinite flight. It also reframed humanity's place within it. For every observer, there exists a horizon beyond which no information can ever arrive. As the acceleration continues, that horizon draws closer, and the number of visible galaxies dwindles. The universe becomes a collection of isolated islands, each cut off from the others by the swelling of space-time. In such a future, distant civilizations would never know the cosmic past we now glimpse. They would see only their own cluster of stars, unaware that billions of galaxies once shone beyond their reach. This revelation leads to a sobering realization. Cosmic acceleration not only determines the future of space, but also the limits of knowledge itself. As the observable universe shrinks, the evidence of its origins fades. The night sky that once told us the story of the Big Bang will eventually fall silent. Its signals stretched beyond the range of any detector. What remains will be the faint glow of local stars, burning in a universe that hides its own beginning. And yet, within that inevitable isolation lies a strange beauty. The laws of physics that drive this acceleration also make existence possible. Without the balance between gravity and expansion, galaxies would never have formed, stars would never have shone, and life would never have arisen to contemplate its cosmic fate. The same dark energy that ensures the universe's eternal flight is the quiet architect of its momentary brilliance. As astronomers continued to map the heavens, the evidence for an accelerating cosmos deepened. Telescopes peered farther into the past, revealing galaxies whose light had traveled for billions of years. Each observation traced a line across time, marking how the universe expanded at different epochs. The pattern was unmistakable. After an early period of deceleration, driven by gravity, the rate of expansion began to increase. Somewhere around 5 billion years ago, dark energy overtook matter as the dominant influence on the cosmos. From that moment onward, acceleration became the law of the universe. To describe this mathematically, cosmologists use Einstein's field equations of general relativity, which link the geometry of space-time to its energy content. When a cosmological constant is added, the equations predict that space will expand exponentially slowly at first, then faster as dark energy dominates. This prediction matches observations with remarkable precision. It tells us that the fate of the cosmos is determined not by the mass of galaxies or the pull of gravity, but by the mysterious pressure of the vacuum itself. Dark energy does not behave like any familiar substance. It exerts a form of negative pressure, meaning it pushes rather than pulls. Where matter clumps together, dark energy spreads evenly throughout space. It does not gather in halos or filaments. It exists uniformly, woven into the geometry of the universe itself. This difference explains why galaxies and clusters remain bound, while the vast expanses between them grow larger with time. Dark energy's influence is subtle on small scales, yet overwhelming across cosmic distances. Some scientists have proposed alternative explanations. Perhaps our understanding of gravity breaks down on the largest scales, or perhaps the acceleration is caused by an evolving field rather than a constant vacuum energy. These ideas are studied through observations of baryon acoustic oscillations, gravitational lensing, and the cosmic microwave background. Yet so far, all the data continue to favor the cosmological constant, a constant energy density that drives eternal expansion. This convergence of evidence has made LCDM the cornerstone of modern cosmology, though it remains a model full of unanswered questions. The discovery of cosmic acceleration changed not only cosmology but philosophy. It forced us to confront the possibility that the universe has no ultimate center or boundary, and no final destination we can reach. The fabric of reality itself is in motion, stretching everything apart. Light emitted from distant galaxies today may never reach us, because the space between us and them expands faster than light can travel. The universe contains regions forever beyond our reach, not because of distance, but because of time's own geometry. These are cosmic horizons, invisible boundaries that define the limits of what can ever be known. As the acceleration continues, more galaxies will cross this horizon, vanishing from view. Their light, stretched to infinite wavelengths, will fade into darkness. The observable universe will become smaller, even as the total universe grows larger. From the perspective of a future observer, billions of years hence, the cosmos will appear nearly empty. Only the stars of their local group will remain, shining in an otherwise featureless void. They will live in a universe without cosmic background radiation, without visible galaxies, and without the clues that reveal the universe's true age and origin. For us, living at this brief and privileged moment in cosmic history, the evidence is still within reach. We can still detect the faint glow of the cosmic microwave background, still measure the redshift of distant galaxies, and still observe the expansion that defines our universe. This ability will not last forever. Cosmic acceleration is steadily erasing the traces of the past, hiding the story of creation behind a horizon of silence. Yet, there is a profound symmetry in this process. The same laws that brought the universe into being continue to govern its evolution. Gravity and expansion, matter and energy, attraction and repulsion, all are aspects of a single cosmic equation written into space-time. Dark energy may be mysterious, but it is not alien to nature. It is part of the same universe that gave rise to stars, life, and thought. When the supernovae of the late 1990s revealed the universe's acceleration, they did more than change cosmology. They reminded us that the universe is not static, not stable, and not finished. It is a living continuum of change, where even the emptiness between galaxies carries power. The discovery of cosmic acceleration was not merely a scientific revelation. It was a moment when humanity glimpsed the true scale of the unknown. And so, as we stare into the darkness between stars, we are not looking into emptiness. We are looking into the force that shapes everything, the quiet expansion of space-time itself. The same expansion that began in the first instant of the universe continues today, carrying galaxies apart, stretching light, and writing the future in ever-widening circles. It is the invisible breath of creation, pushing the cosmos outward toward eternity. The question that now rises from this discovery is both scientific and existential. If space can accelerate endlessly, where does that leave the light that connects us to the distant universe? What happens when even light itself can no longer bridge the growing gulf? There is a limit to how far we can see, and that limit is not set by the power of our telescopes, but by the nature of space itself. Light has a finite speed, and while nothing can move through space faster than light, space itself can expand at any rate. This distinction is the foundation of modern cosmology. The reason galaxies at great distances can appear to recede faster than light without breaking the rules of relativity. It also explains why our view of the universe is bounded by a cosmic horizon, a frontier beyond which no signal will ever reach us. Imagine the universe as an ocean of space stretching in all directions. When light leaves a distant galaxy, it begins a long journey toward us, carried along by the expanding sea. But as space stretches, the wavelength of that light stretches too, becoming redder and weaker with every passing billion years. At great distances, the expansion of space pulls galaxies away faster than light can cross the gap. The photons they emit can never make up the distance. They are carried away with the expanding fabric of the universe itself. Those galaxies vanish beyond our event horizon, not because they cease to exist, but because the universe denies us their light. This is not the same as the boundary of the observable universe, which represents the farthest distance light has reached us since the Big Bang. The observable universe is about 93 billion light-years in diameter, a sphere defined by time and the speed of light. The cosmic event horizon, however, marks a different kind of limit, the point beyond which light emitted now will never reach us in the future, no matter how long we wait. It is not a wall in space, but a boundary in time. What lies beyond it will forever remain unobservable. This distinction is subtle but profound. The observable universe grows with time because as the universe ages, light from more distant regions finally arrives. But the event horizon defines the future, the ultimate reach of causality. In a universe dominated by dark energy, that horizon is fixed at roughly 16 billion light-years. Anything farther than that will recede too quickly for its light to ever reach us. As the expansion accelerates, more galaxies cross that boundary each year, disappearing one by one into eternal darkness. The discovery of these horizons forces us to rethink the meaning of distance and time. When we look at a galaxy 10 billion light-years away, we are not seeing where it is today, but where it was when the light began its journey. In the billions of years since, the space between has expanded enormously. The galaxy we observe might now be 40 or 50 billion light-years distant, carried far beyond our ability to see it again. The deeper we look, the farther back in time we peer, until our gaze reaches the cosmic microwave background, the oldest light we can ever observe. emitted when the universe was only a few 100,000 years old. Beyond that wall, there is no light, only the opaque glow of the infant cosmos. The expansion of space not only limits what we can see, it also determines what we can influence. Gravity and light both travel at finite speeds, so beyond the event horizon, no signal from us can ever reach. The universe is not infinite in what it allows us to know or change. It is divided into causally disconnected regions, each isolated by the acceleration of expansion. These horizons are like cosmic borders drawn not by matter but by time itself. Redshift is the evidence of this stretching universe. As galaxies recede, their light shifts toward longer wavelengths, moving from blue to red to infrared and beyond. The greater the redshift, the faster the galaxy is moving away, and the farther back in time we are seeing it. Measurements of redshift form the backbone of observational cosmology, allowing scientists to reconstruct the universe's history of expansion. Every photon that reaches us carries a record of the stretching of space through which it has traveled. This stretching is not limited to light. It affects everything not held together by gravity or other forces. The large-scale structure of the universe, filaments of galaxies and voids between them, grows thinner with time as space expands. Even within galaxy clusters, the tug of dark energy subtly alters the balance of gravity. Over trillions of years, these clusters will drift apart, their mutual connections lost. The sky of the far future will hold fewer and fewer galaxies, until only the nearest remain visible. And as the horizon draws inward, the universe becomes a stage of shrinking knowledge. Future astronomers, living in isolated galaxies, will not be able to detect the cosmic microwave background or measure redshifted light from distant systems. They will have no evidence of cosmic expansion, no clue that their island of stars was once part of a vast and connected cosmos. To them, the universe will appear static and eternal, the same illusion humanity once held before we learned to measure the faint drift of galaxies. The irony is striking. The more the universe expands, the less it reveals. As space grows beyond light's reach, the boundaries of the knowable cosmos tighten around us. We live in an era uniquely balanced between past and future, far enough from the Big Bang to see its echo, yet early enough that the sky is still filled with galaxies. To understand cosmic horizons is to realize how brief this window of cosmic awareness truly is. The idea that parts of the universe are already lost to us is not poetic exaggeration, but a measurable truth. The light from galaxies beyond a certain distance will never reach Earth. Not now, and not in any future. Those regions are receding faster than light can travel, carried outward by the stretching of space. This does not break any law of physics, because relativity forbids only motion through space faster than light, not the growth of space itself. The metric of space-time, the coordinate system by which we measure distance, is expanding. Galaxies remain still in their local frames, while the universe between them swells endlessly. As the expansion continues, light from ever more distant regions is drawn to longer wavelengths. Its energy weakens, its frequency slows. What once began as a brilliant visible beam becomes infrared, then microwave, then radio, and eventually fades into unobservable wavelengths. The light never stops traveling. It simply becomes so stretched that it no longer carries usable information. The cosmic microwave background itself, the faint relic of the early universe, is slowly cooling as space expands, its photons redshifting into longer and longer wavelengths. In the far future, this ancient radiation will be undetectable, stretched beyond any conceivable instrument's reach. The concept of cosmic horizons, though abstract, has real consequences. It defines a universe where observation has limits, where not everything that exists can ever be known. Cosmologists often speak of the observable universe as if it were the entire cosmos, but it is only a small region within a much larger reality. The true universe may extend infinitely, or it may curve back upon itself like the surface of a sphere, yet we will never know for certain because light and time confine our vision. We are cosmic observers, trapped within a finite window, peering outward into a darkness that forever recedes. At its heart, a horizon is not just a limit of space, it is a boundary of cause and effect. Imagine two galaxies separated by such an immense distance that light from one can never reach the other. No matter how powerful the signal, no exchange of energy or information is possible. In practical terms, they occupy separate universes, each isolated by the accelerating expansion. These disconnected regions are sometimes called causal patches. Every observer lives within one, defined by the reach of light over all time. Even if the larger universe continues without end, each causal patch becomes a self-contained domain, its inhabitants forever cut off from everything beyond. Within our causal patch lies everything we will ever know: the galaxies we can observe, the cosmic microwave background that surrounds us, and the local group of galaxies bound together by gravity. Beyond it, the rest of the universe remains real but unreachable. This isolation will deepen as cosmic acceleration progresses. The Andromeda Galaxy, now approaching us, will eventually merge with the Milky Way to form a single, massive, elliptical galaxy, often called Milkomeda. Around it, the other members of the local group will remain gravitationally tied, but all more distant galaxies will drift beyond the event horizon, taking with them the evidence of the larger cosmos. In that distant age, when the observable universe has shrunk to a few tens of millions of light years, the night sky will appear quiet and sparse. There will be no trace of the cosmic web of galaxies that once filled the heavens. The cosmic microwave background will have faded to wavelengths longer than the diameter of a galaxy. The descendants of future civilizations, if they exist, will look up and see only their own stars, unaware that their home was once part of a grander structure. To grasp this vision is to understand how the expansion of space shapes not only the universe's future, but also our perception of reality itself. Even now, the most distant galaxies we see are snapshots from a younger cosmos, frozen in time by the limits of light. Each photon we detect is a messenger from an age when the universe was smaller, denser, and hotter. We cannot see these galaxies as they are today. We see them as they were billions of years ago, because light takes time to arrive. The deeper we look, the further back in time we travel, until vision itself becomes a form of archaeology, uncovering layers of cosmic history. And just as there is a limit to what we can see, there is a limit to how far back we can look. Before the cosmic microwave background was released, the universe was opaque, filled with free electrons that scattered light. Beyond that wall lies an unobservable realm, the first few 100,000 years after the Big Bang, when radiation and matter were inseparable. To explore that era, scientists use indirect evidence, studying gravitational waves and particle relics that carry information from before light could travel freely. In doing so, they push against the boundaries of the horizon, searching for the faintest echoes of a time no telescope can ever view. The knowledge that the universe contains unreachable regions is both humbling and profound. It reminds us that observation has an end, that even light, the fastest messenger in existence, is finite against the scale of cosmic expansion. The sky we see is not a map of the whole, but a fleeting window through which we glimpse the universe's vastness before it slips beyond our reach. Over billions of years, the cosmic horizon will continue to retreat, like a tide pulling away from the shore of observation. Galaxies that are visible today will slowly fade as their light stretches into undetectable wavelengths. The rate of this loss is not constant, but accelerates with time, driven by the steady influence of dark energy. Each moment, more of the universe vanishes beyond the event horizon, not through destruction, but through disconnection. The cosmos, in its expansion, is erasing its own memory. Even now, this process is underway. Roughly every year, hundreds of galaxies slip beyond the edge of what will ever be observable. Their light, still traveling toward us, is stretched thin by the swelling of space, weakening into faint whispers of its former brilliance. In future epochs, the sky will appear emptier, the distances between visible galaxies greater. Astronomers of that far time would find themselves in a universe that seems static and small, unaware that the darkness beyond once shimmered with billions of galaxies. The evidence of the Big Bang, the redshift, the cosmic microwave background, and the distribution of galaxies will all have faded from view. The concept of a cosmic horizon also redefines our sense of time. In general relativity, space and time are intertwined. When one stretches, the other dilates. The expansion of space is not separate from the flow of time, but part of the same cosmic geometry. As light travels through expanding space, its wavelength grows, and its energy decreases. This redshift is not merely a Doppler effect caused by motion, it is a record of time itself stretching. Each photon carries with it the history of the universe's expansion, encoded in its lengthened wavelength. In this way, the universe is a dynamic archive of its own evolution. The further we look, the deeper into its past we peer, and yet, at the same time, we witness its future, the inevitable isolation that expansion brings. Beyond our horizon, regions of space may contain countless galaxies, perhaps even civilizations, yet they will remain forever separated from us by the growth of the universe itself. It is a reminder that space is not an empty backdrop, but an active participant in cosmic destiny. Astronomers define several types of horizons to describe these limits. The particle horizon marks the maximum distance from which light has reached us since the beginning of time, essentially the edge of the observable universe. The event horizon defines the distance beyond which light emitted now will never reach us. There is also the Hubble horizon, a measure related to the present rate of expansion. Each of these boundaries describes a different aspect of how light, time, and expansion interweave. Together, they form the map of what is knowable and what lies forever beyond. Understanding these horizons transforms the way we think about reality. The universe we inhabit is finite in what it allows us to perceive, even if its total extent may be infinite. The sky is not a panorama of all existence, but a cross-section of space-time, a thin slice visible through the narrow lens of causality. Every telescope, no matter how powerful, peers only into the part of the cosmos that light has had time to reach from. The rest remains hidden, perhaps forever. Still, this limitation is not a failure of knowledge, but a revelation of nature's order. The same laws that prevent us from seeing beyond the horizon also protect the consistency of physics across all scales. The constancy of the speed of light, the fabric of relativity, and the geometry of space-time are what make understanding possible at all. They are the structure within which meaning itself can exist. The horizon is not an end but a boundary condition, the edge of what can be known from any one point in the universe. In a strange way, these cosmic limits give the universe its beauty. They remind us that knowledge, like light, must travel through time, and that there are places even thought cannot yet reach. To gaze at the night sky is to look across both space and time, into a vastness that forever outruns us. The galaxies at the edge of visibility are not distant in the way mountains are distant. They exist in another era, receding into the unseeable future. When we observe them, we are witnessing the last messages they will ever send, the final photons, escaping before expansion stretches them beyond reach. Their light is a farewell across eternity, a record of a cosmos still young enough to speak. One day, those messages will fade, and the universe will grow silent, not because it ends, but because it has expanded beyond communication. This is the meaning of the cosmic horizon. Not a line drawn in the sky, but the ultimate boundary of connection. Beyond it lies the rest of the universe, infinite and unknowable, continuing to evolve in silence. As we stand beneath our shrinking canopy of stars, we inhabit a privileged moment, one when the universe is still visible, still speaking through its ancient light. For those who come after, the cosmos will be quieter, dimmer, and more mysterious. In the vastness of time, we are the generation that can still see almost everything. And that realization, both humbling and awe-inspiring, leads to the next question in our journey. If expansion hides the universe from itself, what fate awaits the galaxies we can still see today? Every second, the universe grows larger, and with each heartbeat of cosmic time, more of it slips beyond our reach. The galaxies that once shone close enough to study are now fading, their light stretched thin by the accelerating expansion of space. It is as though we are watching the night sky dissolve in slow motion, the stars receding not because they move, but because the space between us and them refuses to stay still. This quiet drift defines the fate of everything we can see, the destiny of the observable universe itself. According to the LCDM model, the same framework that unites dark energy, dark matter, and general relativity, the acceleration will not stop. Dark energy, acting as a constant pressure in the fabric of space, will continue to dominate over gravity, ensuring that expansion never reverses. This does not mean galaxies are literally speeding through space faster and faster, but that the scale of the universe, the distance between all unbound points, continues to grow exponentially. Gravity still holds local regions together, yet beyond those bounds, the pull of dark energy is unrelenting. Our local group of galaxies, containing the Milky Way, Andromeda, and a few dozen smaller companions, is small enough for gravity to overcome expansion. In roughly 5 billion years, the Milky Way and Andromeda will merge into a single, massive elliptical galaxy, often referred to as Milkomeda. Around it, smaller galaxies, like the Triangulum, will fall inward, their orbits collapsing into this new structure. Beyond that small island of matter, however, all other galaxies will drift away, carried beyond the cosmic event horizon by the steady push of dark energy. In about 100 billion years, distant galaxies will have redshifted so completely that their light will no longer reach the combined Milkomeda galaxy. The night sky, once filled with hundreds of billions of galaxies, will become a sparse field of local stars. To the astronomers of that distant age, the universe will appear static. They will see no trace of cosmic expansion, no evidence of the Big Bang, and no sign of the ancient cosmic microwave background that once filled the heavens. Without those clues, they may never know that the universe was born from a single, hot, dense beginning. The cosmos will have erased its own history. This is the ultimate isolation, a cosmic solitude written into the equations of expansion. The future universe will be divided into countless, gravitationally bound regions, each surrounded by an infinite dark void. Every island of matter will become its own self-contained cosmos, unable to exchange light or information with the others. Time will continue, but the universe will have lost its visible unity. It will no longer be one connected web of galaxies, but a scattered archipelago of light, adrift in an endless sea of darkness. The cosmic microwave background, our greatest window into the early universe, will also fade into invisibility. Its wavelength, already stretched into the microwave range by billions of years of expansion, will continue to lengthen until it exceeds the diameter of any possible detector. The temperature of this radiation, now about 2.7 degrees above absolute zero, will cool further to less than a trillionth of a degree. It will merge with the faint thermal radiation of interstellar dust, becoming indistinguishable from the silence of the vacuum. As the universe grows darker, the balance of energy will shift. Star formation will slow, because galaxies will exhaust their reservoirs of gas. The great cosmic factories that once produced light and heat will fall silent, their remaining stars aging into red dwarfs and white remnants. The night sky will glow faintly with these dim embers for trillions of years before they, too, fade. The galaxies of that time will be quiet and red, filled with ancient stars and surrounded by blackness. Even the expansion itself will continue to accelerate, ensuring that no new light from beyond the local horizon can arrive. The future astronomers of Milkomeda, if they exist, will see only a static universe composed of their own stars. They will have no way to know that beyond the darkness, space continues to grow, carrying untold galaxies into the unreachable distance. Their instruments may detect nothing but silence beyond their own domain. And yet, this fate is not a tragedy, but an inevitable consequence of the laws that govern existence. The same expansion that isolates galaxies is the reason stars and planets could form in the first place. Without it, the universe would have collapsed under its own gravity long ago. Cosmic acceleration ensures survival in one sense, and solitude in another. It grants time but takes away contact, preserving the local while erasing the distant. To understand the fate of the observable universe is to recognize the duality of creation and disappearance. The same process that allows stars to shine also guarantees that their light will one day fade beyond the reach of all observers. The universe, it seems, is both an exhibition and a vanishing act, revealing its wonders for a brief cosmic moment before hiding them forever behind an expanding horizon. Yet this vision of the future, though lonely, is not without beauty. The stars that remain will still burn for trillions of years, their light crossing the silent dark to illuminate small corners of space. The story of cosmic expansion, even as it erases the distant universe, leaves behind the memory of everything that came before. In that memory lies the ultimate paradox that to exist within a universe that expands faster than light is to live in a cosmos that is both infinite and fleeting at the same time. In the far reaches of time, long after the galaxies beyond our local group have vanished beyond the cosmic horizon, the universe will enter a deep stillness. The stars of Milky will continue to burn, though fewer will be born with each passing epoch. Hydrogen, the fuel of stellar life, will grow scarce. The great spiral patterns of galaxies will fade into diffuse ellipses of red and orange light as new generations of stars cease to form. The once vibrant cosmic web will be reduced to quiet clusters of matter, islands of gravity surrounded by the boundless dark. For the first few trillion years, this will be a time of subtle decay rather than destruction. Red dwarf stars, the longest living in the cosmos, will glow faintly across the ages. Their light will be cool and dim, yet steady, stretching out the era of visible starlight for as long as possible. But even these small suns will eventually exhaust their hydrogen and fade into black dwarfs, cold, invisible remnants of what once was. The universe will enter a phase astronomers call the degenerate era. In this age, the luminous universe will have ended. The night sky will no longer sparkle with new light, but will glow faintly from the residual heat of white dwarfs, neutron stars, and slowly evaporating black holes. Matter itself will persist, but motion will slow. Collisions between remnants will grow rare as the vast distances between stars increase. The temperature of the cosmos will approach absolute zero, and entropy, the measure of disorder, will climb toward its maximum. Entropy is the quiet architect of cosmic fate. It is not destruction, but the natural progression toward balance. In the early universe, energy was concentrated in bright, hot regions, stars, galaxies, and nebulae. Over time, these concentrated sources of order dissipate their energy into the surrounding environment. Heat flows from hot to cold until no gradient remains, until the entire universe becomes uniform and featureless. This is the essence of thermodynamics, the arrow of time that leads all structure toward stillness. Even the mightiest structures will yield to this law. Galaxy clusters, held together by gravity, will gradually lose their members. The gravitational pull of the cluster will weaken as stars die and dark energy stretches the space between them. Galaxies will drift apart, like faint embers carried by an invisible wind. The last interactions between galaxies will end as the universe expands faster than they can meet. After 100 trillion years, the age of stars will end completely. Black holes will dominate the remnants of the cosmos, anchoring what remains of galaxies in deep gravitational wells. Around them, stray planets and stellar corpses will circle in long, slow orbits. Occasionally, one will drift too close and be consumed, releasing a final burst of light before falling silent forever. Yet even black holes are not eternal. According to Stephen Hawking's theory, they radiate energy slowly through a process now known as Hawking radiation. Over unimaginably long timescales, this radiation causes black holes to lose mass and eventually evaporate. The largest black holes, the giants at the centers of galaxies, may take up to 10 to the power of 100 years to disappear. When they do, the universe will have entered the black hole era, a dark epoch illuminated only by the faint glow of evaporating horizons. Each dying black hole will release a whisper of radiation into the vast cold, adding to the ever-thinning sea of low-energy photons that fills the universe. This slow evaporation marks the final transformation of concentrated energy into entropy, the closing of the last bright chapters of cosmic history. The fate of the observable universe is therefore not a single moment of collapse or explosion, but a gradual, graceful fading. The cosmos will not end in violence but in silence, dissolving into uniformity as energy spreads evenly through an ever-expanding void. This outcome is not speculation. It arises naturally from the same physical laws that govern stars, light, and matter. The same equations that describe the rise of galaxies also predict their eventual disappearance. To think of this future is to recognize the fragility of existence. Every atom, every photon, and every spark of consciousness exists in defiance of the slow drift toward equilibrium. The structures we see, from stars to living beings, are temporary reversals of entropy, local moments of order within a universe that trends toward calm. Yet these fleeting moments are the very essence of meaning, the brief patterns carved into the vast and indifferent flow of time. In that distant age, when the last black holes fade and the universe cools into stillness, there may be no witnesses left to see it. But the laws that guide that ending are already written in the expansion we observe today. Each galaxy receding beyond our reach is a note in the long symphony of cosmic evolution, a composition that began with a burst of light and will end in eternal quiet. As we gaze at the sky today, filled with stars and distant galaxies, we are seeing the universe at its most vivid. The future that awaits is not one of collapse but of solitude, an ever-widening silence where light itself grows faint. And yet, in that silence lies the enduring legacy of creation, that from chaos came order, from darkness came brilliance, and from expansion came the very stage upon which existence could unfold. The universe's distant future is not marked by catastrophe, but by an almost imperceptible unwinding. As time stretches onward, the familiar structures of the cosmos dissolve, leaving behind a scene that defies imagination, a space nearly empty, a silence deeper than anything we can conceive. And yet, this silence will be the direct descendant of the same physical laws that shaped the brilliant, dynamic universe we inhabit today. When the last of the starlight fades, the Milky galaxy will drift through the dark, surrounded by an expanding emptiness. The cosmic background radiation, once glowing in microwaves, will be stretched to wavelengths longer than any planet, effectively disappearing into the static of space. The temperature of the universe will approach absolute zero, so low that motion itself will slow to a crawl. Even the faint warmth left over from the Big Bang will be gone, replaced by a universe that has become almost perfectly still. Stars will no longer form, for the raw material hydrogen and helium will have long been exhausted. The few remaining red dwarfs will cool into black dwarfs, objects that emit no light, no heat, and no signal to announce their existence. Planets, long frozen, will wander orphaned through the dark, pulled by the faint gravity of the black dwarfs they once orbited. Every spark of light that once filled the universe will have gone out, leaving behind only the cold geometry of space. Black holes will continue to dominate the cosmic landscape, but they, too, are subject to decay. Through Hawking radiation, they emit tiny amounts of energy, losing mass so slowly that the process spans timescales beyond comprehension. Over trillions upon trillions of years, these dark giants will shrink, their event horizons collapsing inward. The final moments of their evaporation will be marked by a brief burst of faint radiation, the last act of luminosity in a universe that has forgotten what light is. After the last black hole evaporates, matter itself will begin to disintegrate. Protons, once thought to be eternal, may decay over timescales of around 10 to the power of 34 years or longer, depending on physical models not yet confirmed. If proton decay occurs, the universe will transition into the dark era, a realm without atoms, without stars, without structure. The only things left will be photons, neutrinos, and the faint remnants of what were once the building blocks of matter. These particles will drift endlessly through expanding space, rarely interacting, each carrying a fragment of the universe's final entropy. By this time, even the concept of time will lose its meaning. In a cosmos devoid of events, motion, and energy exchange, time has no markers. There will be no change to measure, no cause or consequence to distinguish one moment from another. The universe will exist in a state of thermal equilibrium, where all gradients have vanished. The laws of thermodynamics will have run their full course. This fate is known as the heat death of the universe, not a fiery end, but a cooling into uniform stillness. Every atom, every photon, every trace of motion will have settled into perfect balance. Entropy will have reached its maximum value, and with it, the capacity for new change will have ceased. The cosmos will not collapse, nor will it explode. It will simply endure vast, silent, and eternal in its quiet decay. To human minds, built to find meaning in cycles of life and renewal, such an ending feels haunting. Yet, it is not an annihilation, but a transformation. The energy that once powered stars and galaxies will still exist, diffused evenly across space. The universe will persist, but its story, the drama of creation and structure, will have ended. The same equations that predict expansion, the same constants that govern gravity and light, lead naturally to this state of equilibrium. The end of structure is not a failure of physics, but its fulfillment. From the first instant of cosmic inflation to the last whisper of Hawking radiation, the universe has followed a seamless trajectory: expansion, formation, decay, and stillness. This continuity is profound. It means that every moment, from the birth of galaxies to their final fading, is part of one unbroken pattern. The cosmos has never ceased to evolve. It has only changed the form of its activity. Even in the universe's final darkness, quantum physics may prevent absolute silence. Quantum fluctuations, tiny, spontaneous variations in energy, will continue to ripple through the vacuum. These fleeting disturbances may create virtual particles that flicker in and out of existence, a reminder that even nothingness is never truly nothing. The same uncertainty that shaped the early universe still lingers in its end. Thus, the fate of the observable universe is a mirror of its origin. It began in a burst of unimaginable energy and will end in a whisper of uniform calm. From expansion faster than light to infinite stillness, the cosmos completes its circle, not in destruction, but in balance. The laws of physics, unbroken from beginning to end, remain the only constant. And yet, the question persists: is this truly an ending, or merely another transformation hidden beyond our horizon of understanding? Could new universes arise from the quantum vacuum, as ours once did from the energy of inflation? Or will this silence last forever, a frozen eternity without a spark? The answers may lie forever beyond our reach, but as we contemplate this vast timeline from the first flicker of light to the final whisper of darkness, we are reminded of the rare moment we occupy now, a universe still bright enough to see itself. If the universe continues to expand faster and faster, one may wonder whether this process has an ultimate limit. Can space stretch forever without consequence? Or is there a boundary beyond which even the laws of physics begin to fracture? To explore this question, cosmologists have proposed a series of theoretical models describing the distant future of an accelerating universe. Among them is one of the most striking possibilities ever imagined: the Big Rip. The Big Rip arises from a hypothetical form of dark energy known as phantom energy. In the simplest cosmological models, dark energy behaves like a constant. Its density remains the same, even as space expands. But if this energy were to grow stronger over time, increasing its density as the universe grows, then the acceleration would not simply continue, it would intensify without limit. The expansion would become so rapid that eventually it would overcome all other forces: gravity, electromagnetism, even the binding energies within atoms themselves. This model depends on a number known as the equation of state parameter, written as W. In standard cosmology, where dark energy behaves like a cosmological constant, W equals -1. If W is greater than -1, the universe's acceleration slows over time. But if W drops below -1, the density of dark energy increases as the universe expands and the path to the Big Rip begins. In such a scenario, every structure in the cosmos is ultimately torn apart by the relentless growth of space itself. The concept was explored in detail in 2003 by the physicist Robert Caldwell and his colleagues Mark Kamiankowski and Nevin Weinberg. They calculated the stages of cosmic destruction that would follow from this runaway acceleration. First, galaxy clusters would disband as the dark energy repulsion overcomes their gravitational bonds. Then individual galaxies, such as the Milky Way, would be ripped apart. Later, star systems would be unbound, planets flung into the void, and finally, atoms themselves would disintegrate as the space between subatomic particles expands faster than the forces that hold them together. The timeline of such a cosmic apocalypse depends on the exact value of W. If W were only slightly below -1, the universe could continue as it is for tens of billions of years before any catastrophic effects appear. But as W decreases further, the end approaches sooner. In the most extreme versions, the universe could end within a few billion years of the present, though current data show no evidence for such rapid instability. Observations from the Planck satellite, along with measurements of type Ia supernovae and baryon acoustic oscillations, suggest that W is remarkably close to -1, with little sign of variation. This implies that dark energy is either a true cosmological constant or something behaving very much like it. In that case, the universe's expansion will continue forever, but without tearing itself apart. Galaxies will drift away, stars will die, and space will grow cold, but the fabric of reality will remain intact. The Big Rip remains a theoretical possibility, not an imminent threat. Still, the model carries profound implications. It reveals that the fate of the universe depends on a single number, the precise value of W. If it ever drifts below -1, even by the smallest amount, then cosmic expansion becomes not just eternal, but destructive. The calm, graceful fading of the universe described by the heat-death model would be replaced by a violent disassembly of all structure. The cosmos would not drift into silence, it would end in chaos. The Big Rip also demonstrates how intimately the universe's destiny is tied to the nature of dark energy. If dark energy is truly a constant, the cosmos will expand forever, in peace. If it evolves, if its strength changes with time, then the future may unfold in ways we cannot yet imagine. To determine which version of reality we inhabit, astronomers continue to measure the expansion rate of the universe with increasing precision. Future missions like the Nancy Grace, Roman Space Telescope, and the Euclid Observatory are designed to refine the value of W and test whether dark energy remains constant or evolves with time. Beyond the Big Rip, other theoretical models offer different endings. Some propose that dark energy could decay, reversing acceleration and leading to a slow contraction, a future known as the Big Crunch. Others imagine oscillating universes that expand and collapse in infinite cycles. Though these models find little support in modern data, there are also speculations that dark energy might fluctuate, leading to alternating periods of acceleration and deceleration. Each of these ideas reveals a different possible rhythm of the cosmos, but all share a common foundation: that the universe's ultimate fate is governed by the properties of the vacuum itself. In every version, one truth remains: the universe is not static. Whether it ends in a distant fading or a sudden rupture, it is forever evolving, driven by the deep geometry of space-time. Even the calmest night sky hides a silent acceleration, a tension written into the structure of existence. The question is not whether the universe will change, but how. The Big Rip stands as the most extreme expression of that change, a reminder that the laws governing the largest scales of the cosmos also dictate the smallest. If the expansion of space can eventually overcome the forces that bind atoms, then the universe itself is not immune to its own momentum. It is a thought both terrifying and majestic, that the same gentle expansion that separates galaxies today could one day unweave the very fabric of matter. The deeper scientists probe into the mystery of dark energy, the more they realize that the universe's future is suspended on a knife's edge between stability and chaos. If the cosmological constant truly governs expansion, then the future will unfold slowly, gently, and indefinitely. But if dark energy is more dynamic, an evolving field rather than a constant, then its behavior could change, setting into motion cosmic transformations more dramatic than we can yet measure. One such possibility is the scenario of quintessence, a model in which dark energy behaves not as a fixed property of the vacuum, but as a dynamic energy field that evolves through time. Unlike the cosmological constant, which remains uniform and eternal, quintessence can grow stronger or weaker, depending on the evolution of the universe itself. In this view, dark energy is more like a fluid that changes its pressure as space expands. If its energy density decreases with time, the universe's acceleration could eventually slow or even stop, leading to a gentle, asymptotic expansion. But if its density increases, it could grow more dominant, potentially steering the cosmos toward the catastrophic path of the Big Rip. The quintessence model is elegant because it connects dark energy to ideas already present in particle physics. It imagines a scalar field, a kind of invisible ocean pervading space, whose potential energy drives cosmic acceleration. This is reminiscent of the inflationary field thought to have powered the universe's rapid growth in its first instant. The difference lies in scale and persistence. Inflation acted for only a fleeting moment, while quintessence could operate over billions of years. Some physicists have suggested that the two phenomena may even be related, that the field which once sparked inflation might have decayed into the dark energy that now drives the universe's late-time expansion. Testing such models is extraordinarily difficult. The effects of dark energy are subtle, noticeable only across vast cosmic distances and timescales. Astronomers rely on precise measurements of type Ia supernovae, baryon acoustic oscillations, and the cosmic microwave background to infer its properties. Even tiny deviations from W equals -1 could reveal whether dark energy evolves or remains constant. So far, all evidence points towards stability, but the uncertainty remains large enough that scientists cannot rule out a slow change. The universe, it seems, still guards its secret closely. Another idea that challenges the permanence of dark energy is the possibility of vacuum decay. In quantum field theory, the vacuum, what we call empty space, is not necessarily the lowest possible state of energy. It may be a false vacuum, a metastable condition that could, in principle, collapse to a lower energy level. If such a decay occurred, it would release enormous energy, transforming the structure of space itself. The universe would undergo a phase transition, much like water freezing into ice, but on a cosmic scale. This event would create a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics as it passes. Such an event, if it were to happen, would be unstoppable. There would be no warning, no sign, and no survivors. The bubble would convert everything in its path, atoms, stars, galaxies, into whatever form the new vacuum permits. Yet, The timescales for such decay, according to current estimates, are staggeringly long, far exceeding the age of the universe by many orders of magnitude. Most physicists consider this scenario an intriguing theoretical curiosity, rather than an imminent concern. It serves, however, as a reminder that the universe's stability is ultimately a question of quantum mechanics, that even the emptiness between galaxies may contain potential for change. Between these extremes, the slow fading of heat, death, the violent disassembly of the Big Rip, and the sudden transformation of vacuum decay, the future of the cosmos spans a spectrum of possibilities. All are consistent with known physics, yet each depends on small details of dark energy's nature that remain hidden. It is remarkable that the universe's destiny could hinge on a parameter as simple as W, a single number describing the relationship between pressure and energy density. This delicate sensitivity is part of the beauty of cosmology. The same equations that describe the growth of galaxies and the curvature of space-time also determine the final act of cosmic evolution. The cosmos is both vast and fragile, governed by laws that are at once simple and profound. Every observation, every photon we detect, helps narrow the possibilities, refining our picture of what lies ahead. In the meantime, expansion continues. Galaxies recede, horizons grow smaller, and dark energy quietly shapes the future. Whether it remains constant or changes over time, it is the dominant force in the universe today, the silent architect of its destiny. Humanity stands at a rare moment, able to measure the acceleration of the cosmos and speculate about its farthest future, yet unable to influence even a single atom of that outcome. Perhaps that is the most humbling truth of all. The universe is not ending tomorrow, nor even in any timescale comprehensible to life. Its fate will unfold over unimaginable epochs, written not in fire, but in the slow geometry of expansion. And still, we wonder what lies beyond that final silence, whether the same quantum restlessness that filled the void with light once before might someday awaken again. Across the immense silence of cosmic time, the universe balances on a delicate threshold between infinite expansion and eventual dissolution. The theories that describe its far future differ in scale and tone, yet all begin from the same truth that dark energy, whatever its origin, defines the ultimate shape of existence. Whether constant or evolving, it governs the rhythm of the cosmos, deciding whether space will stretch gently forever or erupt into a final, catastrophic disassembly. If dark energy remains perfectly constant, the universe settles into an eternal acceleration. Galaxies drift apart, stars die, and the cosmos cools toward the quiet equilibrium known as heat death. This is the future most consistent with present data, a universe expanding smoothly, endlessly, and peacefully. But if dark energy grows stronger with time, the picture changes dramatically. The expansion would accelerate exponentially, leading to the Big Rip. The differences between these outcomes may be small in mathematics, yet they define entirely different destinies. One a gradual dimming, the other a cosmic storm that tears space apart. To imagine the Big Rip more closely is to confront the limits of physical law. As dark energy strengthens, it begins to overcome gravity at ever smaller scales. Galaxy clusters dissolve first, their members flung into the darkness. Later, individual galaxies, such as the Milky Way, lose their cohesion. Stars are stripped from their orbits and wander alone through the expanding void. When the dark energy density exceeds the gravitational binding of a star system, planets drift away from their suns, their orbits stretch to infinity. Eventually, the same effect reaches the atomic scale. The electromagnetic force, which binds electrons to nuclei, is overwhelmed. At that instant, atoms themselves unravel. The universe does not end in fire or collapse, but in a quiet tearing, an expansion so extreme that structure itself becomes impossible. Caldwell and his collaborators estimated that, if W was slightly below -1, the Big Rip could occur about 20 billion years from now. The exact timing depends on how far below -1 the true value lies. Yet current observations suggest that W may be equal to -1 within experimental uncertainty, leaving little room for this catastrophic outcome. Even so, the theoretical framework of the Big Rip provides valuable insight. It shows that cosmic expansion, though serene on human timescales, can in principle reach magnitudes capable of unmaking the universe itself. Other variations of dark energy propose softer but still dramatic endings. In the Little Rip scenario, expansion accelerates indefinitely without ever reaching a finite moment of destruction. Instead of a sudden tearing, gravitational bonds weaken gradually until even atoms can no longer remain bound. In this vision, disintegration occurs not in a single cosmic instant, but over an infinite stretch of time. A related idea, the pseudo-rip, predicts that acceleration increases for a time before leveling off, leaving galaxies isolated but intact. These models, while speculative, illustrate the sensitivity of the cosmos to small changes in its most fundamental parameters. If, on the other hand, dark energy were to reverse sign, turning attractive instead of repulsive, the universe could halt its expansion and begin to contract. Gravity would slowly dominate again, pulling galaxies together in a process that mirrors the Big Bang in reverse. Eventually, the cosmos could collapse into a single point of unimaginable density, a scenario known as the Big Crunch. In such a model, the universe might oscillate through infinite cycles of expansion and contraction, a cosmic heartbeat echoing through eternity. Yet current observations of dark energy's persistence make this outcome unlikely. Between these extremes lies a deeper philosophical truth. The cosmos is not static, nor has it ever been. The illusion of permanence is only the result of our brief perspective within its immense lifespan. From the earliest flash of inflation to the distant eras of fading light, the universe has always been in motion. Its apparent stillness is the pause between vast changes, the balance between creation and decay. Every galaxy, every star, every atom participates in this continuum of transformation. Physicists often describe this in the language of entropy and geometry. Entropy measures the number of possible states a system can take, the degree of disorder. As the universe expands, the number of possible arrangements of matter and energy increases, and so entropy grows. At the same time, the geometry of space-time changes, stretching to accommodate this increasing freedom. Expansion and entropy are thus intertwined, both manifestations of the universe's drive toward complexity and balance. Whether the cosmos ends in calm or catastrophe, it will do so in accordance with these same principles. The Big Rip, the Big Crunch, and heat death are not competing fantasies, but complementary ways of understanding what the laws of physics allow. They are thought experiments that extend our equations to their farthest possible limits. In every version, the same core ingredients remain: gravity, quantum fields, and the unyielding geometry of space-time. The details may differ, but the symmetry of cause and effect, the harmony of the cosmic equation, endures. And in that symmetry lies a quiet beauty. The universe began with expansion faster than light, and it may end with expansion that again outruns every signal, every particle, every trace of what once was. The same tension between creation and dissolution that gave rise to galaxies may one day unmake them. The story of the universe is therefore not a linear narrative with an end, but a vast and continuous transformation: energy into matter, matter into radiation, structure into silence. Whether the cosmos dissolves in a final rip or drifts into infinite stillness, the outcome is written in the same mathematics that allowed us to understand it. The equations of general relativity and quantum field theory, when extended across eternity, reveal not an apocalypse, but an elegant completion, a universe that fulfills its own laws perfectly. The fate of all things, from galaxies to atoms, is the natural conclusion of the same order that made them possible. And so, even the Big Rip, terrifying though it sounds, is simply another face of cosmic harmony. It reminds us that the laws of physics never break. They only change the stage upon which existence plays out. Expansion may tear the cosmos apart, but it does so in perfect obedience to the geometry written at the beginning of time. As the universe stretches further into the future, its destiny seems to settle, not in violence, but in quiet endurance. The expansion that began in a burst of light will continue endlessly, but the drama of galaxies, stars, and creation will fade into a long twilight of cooling and dispersal. This is the vision known as the heat death, a universe that never collapses, never rips apart, but instead expands so completely that all gradients of energy vanish. In that final calm, no motion, no structure, and no change will remain. To understand this fate, one must return to the second law of thermodynamics, the principle that governs all irreversible processes. It states that in any closed system, entropy or disorder must always increase. The universe as a whole behaves as the ultimate closed system, where energy can neither escape nor enter from outside. From the first instant of inflation to the present day, entropy has been steadily climbing, converting the cosmos from a hot, dense, and ordered state into a colder and more chaotic one. Every star that burns, every galaxy that collides, every particle that interacts, moves the universe closer to equilibrium. At the beginning, the cosmos was full of free energy, energy that could perform work. Gravity gathered matter into stars, which transformed mass into light, driving cycles of creation and decay. Over billions of years, this energy has been radiated outward, dispersing through the growing volume of space. As expansion continues, energy becomes more diluted. The temperature difference between stars and the void decreases, and the capacity for work, the ability to form structure, fades away. Entropy is not a force, but a direction, the arrow of time itself, pointing unerringly toward equilibrium. In the far future, long after the last stars have burned out, the universe will enter the degenerate era. Galaxies will contain only remnants, white dwarfs, neutron stars, and black holes surrounded by cold, inert gas. The light that once filled space will have scattered into faint background radiation. The cosmos will be dim, quiet, and slow. On timescales of trillions of years, even these remnants will change. White dwarfs will cool into black dwarfs, their internal heat radiated away into the dark. Planetary systems will drift apart as gravitational tugs slowly alter their orbits. The once luminous universe will become a realm of invisible relics. Yet the story does not end there. As time stretches beyond imagination, matter itself will continue to decay. If protons are unstable, as many theories of particle physics suggest, then even the atoms that compose these remnants will eventually disintegrate. The decay of protons, though uncertain, would erase the last structures of matter, leaving behind only radiation and subatomic particles. Should protons endure indefinitely, gravity will still reshape the universe. Black holes will consume nearby matter, drawing it past their horizons, where it will be lost to observation. These black holes will dominate the cosmos for unimaginable durations, shaping the final luminous traces of existence. The black hole era will last until even these titans fade. According to Stephen Hawking's theory of quantum evaporation, black holes emit faint radiation due to quantum effects near their event horizons. Over time, this radiation causes them to lose mass. Small black holes vanish quickly, but the largest, with masses billions of times that of the Sun, will take roughly 10 to the power of 100 years to evaporate completely. When the last black hole finally disappears, the universe will be left with nothing but low-energy photons, neutrinos, and stray particles scattered through ever-expanding space. This era, sometimes called the Dark Era, marks the true heat death. The temperature of the universe will approach absolute zero, though never quite reaching it. The background radiation will stretch to wavelengths longer than the size of galaxies, making it effectively undetectable. Entropy will have reached its maximum, meaning all energy is evenly distributed, and no further change can occur. Time, in a practical sense, will lose meaning, for there will be no events to mark its passage. The idea of heat death might seem melancholy, but it is not an ending in the traditional sense. It is the fulfillment of the universe's natural trajectory, the final balancing of all energies and forces. The cosmos will not vanish. It will simply settle into a state where all processes have reached completion. The laws of physics will still hold, but there will be nothing left to act upon them. Space will continue to expand, time will continue to exist, but motion will have given way to stillness. To scientists, this distant fate is not a prophecy of despair, but a profound illustration of consistency. From the moment of the Big Bang, the second law of thermodynamics has guided every transformation. The rise and fall of stars, the birth and death of galaxies, even the fleeting spark of life on one small planet, all are temporary patterns that exist within the grand movement toward equilibrium. Entropy is not destruction. It is the universe's way of balancing its accounts. In that final stillness, even though structure fades, information may persist. Quantum mechanics suggests that the information carried by particles cannot be truly destroyed, only transformed. The echoes of every interaction, every photon, every atom, every gravitational ripple may remain encoded in the fabric of space-time, stretched thin but never erased. The universe, even in its darkest age, would still carry the faint imprint of everything that ever was. Eternal expansion and heat death, therefore, are not the negation of existence, but its completion. The cosmos will not end with an explosion or a collapse, but with a whisper, a vast, cold equilibrium, where time itself is irrelevant. The same expansion that once raced faster than light will continue quietly, forever unfolding the stage upon which all things have played their part. In the unimaginable ages that follow, the universe will continue to stretch, smooth, and cool. Its expansion will never cease, and yet the pace of change will slow until motion itself becomes imperceptible. The cosmic stage will remain vast, but the actors will have long vanished. No galaxies, no stars, no planets, only the silent hum of an almost empty vacuum. This is the era of true cosmic equilibrium, where expansion outpaces every form of activity and the universe approaches perfect stillness. During this eternal twilight, the faint traces of energy, still moving through space, will continue to lose strength. Photons, the particles of light, will be stretched by the growing fabric of the universe until their wavelengths exceed the size of galaxies. Each photon will carry less and less energy, its temperature approaching zero, but never reaching it. The radiation that once filled the cosmos with brightness will become so diffuse that it can no longer be distinguished from the vacuum itself. The universe will be transparent, silent, and almost entirely dark. Though lifeless by our standards, this future cosmos will not be without physics. Quantum mechanics will still operate, guiding the subtle fluctuations that ripple through empty space. Virtual particles, momentary flashes of energy that appear and vanish, will continue to flicker across the vacuum. These fluctuations are a fundamental aspect of quantum fields, ensuring that even in apparent nothingness, energy never truly reaches zero. The same uncertainty that allowed the early universe to emerge from quantum chaos will persist forever, faint and restless beneath the surface of perfect calm. At such timescales, the meaning of duration becomes abstract. A year, a century, or a trillion years lose all distinction when the universe has stretched beyond any measure familiar to us. The few surviving particles will move so slowly that their interactions become rare beyond imagination. Occasional collisions between stray electrons or neutrinos may still occur, but at intervals so vast that they are effectively singular events. These sparse interactions will contribute negligible amounts of entropy, but they will remind us that even in stillness, the laws of physics continue to govern. Cosmologists describe these future epochs with poetic precision. After the degenerate and black hole eras comes the dark era, the final act in the cosmic sequence. The total entropy of the universe will approach its maximum possible value, a state where all usable energy is evenly spread. Temperature differences, which drive every process from chemical reactions to star formation, will vanish. Without temperature gradients, there can be no work, no heat exchange, no flow of energy. The cosmos will be at its most stable and its most static. This is the essence of the heat death. It does not imply destruction, but rather the cessation of evolution. The universe will continue to exist, but without the capacity for new complexity. It will be a cosmos stripped of change, a vast expanse of uniform low-energy radiation and sparse particles. The geometry of space will keep stretching, but the events that once gave meaning to time will have ended. Time itself, as experienced through transformation, will lose all reference. To an observer, if any could exist in such an era, the universe would appear eternal and featureless. Horizons would extend infinitely, but there would be nothing left to observe. The same cosmic acceleration that once separated galaxies will now separate even the faintest quanta of energy, preventing any reunion. The dark energy that drives expansion will ensure that no reversal is ever possible. There will be no new bursts of light, no new beginnings, only the silent unfolding of infinite space. And yet, this outcome is strangely consistent with the very principles that made life and light possible. The universe began in a state of low entropy, a highly ordered configuration that allowed energy to flow and structures to form. The growth of entropy, the gradual leveling of energy, is what enabled stars to burn and matter to assemble. Every act of creation required an imbalance, a difference in temperature or density that could only exist in a young, expanding cosmos. Without entropy increasing, there would have been no time, no evolution, and no awareness. The end state of maximum entropy is simply the other side of the same law, the completion of the same cosmic cycle. Even in this cold, dim future, quantum theory whispers that true emptiness may be impossible. The vacuum itself has energy, the same vacuum energy that drives dark energy today. Whether this energy remains constant or fluctuates, it ensures that the universe never truly stops changing. On the smallest scales, there will always be motion, uncertainty, and the possibility of renewal. Some physicists have speculated that, given infinite time, quantum fluctuations could spontaneously give rise to new regions of space, small pockets of energy that expand into fresh universes, just as ours once did. If such a process occurs, then the heat death is not an ending at all, but a transition, the bridge between one universe and another. What we see as final stillness may instead be the soil from which new creation arises. The cosmos, in this view, never truly dies. It transforms, endlessly cycling between silence and light. Even so, these ideas remain speculative. What can be said with certainty is that the observable universe will fade, its structures dissolving as expansion continues without limit. The stars above us, the galaxies we photograph, the light that travels across billions of years, all will eventually vanish into the stretched horizon of space-time. Yet within that fading lies the ultimate harmony of physics, a universe that fulfills every law it ever obeyed. In the farthest reaches of time, beyond anything our species could ever witness, the universe will enter its final quiet. The story that began in a brilliant explosion will conclude not with a bang or a collapse, but with a whisper of fading energy. This is the vision of eternal expansion, an infinite, ever-stretching cosmos that cools as it grows, spreading its remaining light, so thin that it becomes indistinguishable from the void. It is not an apocalypse, but a slow unwinding of everything that once was bright, structured, and alive. Even as space continues to expand, the fundamental constants of nature will endure. Gravity will remain the weakest but most far-reaching force, binding what little matter remains into sparse collections of remnants. Electromagnetism will still govern the interactions of the last electrons and photons. Though those interactions will be rare beyond measure, the strong and weak nuclear forces will persist, though there will be almost no nuclei left to experience them. The laws of physics will not end with the universe's cooling. They will persist in silence, unbroken, but without subjects to act upon. During this endless expansion, the scale factor of the universe, the measure of its size, will grow toward infinity. Each doubling of size will take longer than the last, stretching the cosmic timeline to incomprehensible scales. The redshift of every surviving photon will increase without bound, turning visible light into radio waves, then into wavelengths larger than galaxies, and finally into vibrations so vast that they cannot meaningfully be called light at all. The cosmos will not go dark abruptly. It will fade so slowly that even the concept of darkness loses definition. Entropy, meanwhile, will approach its ultimate maximum. The universe will have achieved what physicists call thermal equilibrium, where every region has the same temperature and no further energy can be exchanged. At this stage, all processes that depend on differences, chemical reactions, star formation, even gravitational collapse will cease entirely. Motion will persist only as inertial drift, the slow separation of particles across unbounded space. The arrow of time, driven by entropy, will flatten into a near horizontal line. Change will continue only in the most abstract sense, expansion without evolution. For human minds, it is difficult to imagine a universe so vast and so still. Time will stretch to scales that make even trillions of years seem fleeting. A second will have no meaning when there are no rhythms left, no pulses of light, no rotations of planets, no orbits to count. The very concept of duration depends on change, and when change disappears, time becomes geometry, an eternal coordinate with no heartbeat. The universe will not die in the sense of ceasing to exist. It will simply become timeless. In that cold expanse, the last traces of structure may linger as wandering particles or relic gravitational waves. Quantum mechanics insists that absolute zero is unreachable, so there will always be a faint shimmer of activity, the quiet tremor of the vacuum itself. Virtual particles will continue to flicker in and out of existence, forming brief ripples in space-time before dissolving again. These fluctuations are the ghosts of the same quantum uncertainty that gave birth to the universe. Even in endless darkness, they ensure that creation and annihilation never fully stop. This deep equilibrium represents the natural endpoint of a universe governed by unbroken physical law. Every transformation from the fusion in the hearts of stars to the collapse of black holes has been a step toward this balance. Nothing about it defies logic or necessity. The heat death is not failure or decay, it is completion. The cosmos has done what it was always destined to do: distribute its energy evenly, exhaust its potential for work, and achieve the ultimate symmetry between matter and space. And yet, this is not a bleak conclusion. It is a moment of profound coherence. The same equations that describe the birth of light also describe its end. The same entropy that drives decay allows existence to unfold at all. Every pattern, every star, every thought has been part of the universe's journey toward equilibrium. To reach that final stillness is to fulfill the laws that have shaped all things since the first instant of time. If the universe could be aware of itself, this would be its moment of understanding, the recognition that expansion, decay, and silence are all aspects of the same grand design. The cosmos began with energy concentrated in one point and ends with that energy spread perfectly across infinity. The path between those two states is the history of everything. Perhaps, in that quiet future, the vacuum will again stir, and another burst of inflation will ignite a new universe from the remnants of the old. Perhaps not. Either way, the symmetry remains. From nothing came everything, and to everything returns nothing. Eternal expansion is not a defeat. It is the natural pulse of creation. The cosmos does not vanish. It transforms. And so the story of heat death is not the end of wonder, but its continuation into silence, the infinite breath of a universe that has expanded faster than light, and will do so forever, until even the word forever becomes indistinguishable from the stillness it describes. Even in the deepest silence of an expanding universe, emptiness is never truly empty. What appears to be a void, a vast, dark expanse, stripped of stars, galaxies, and light, still seethes with invisible energy. This energy, predicted by quantum field theory, is the heartbeat of the vacuum itself. It flickers constantly, creating momentary bursts of activity, even in the absence of matter. Space, no matter how empty it seems, is alive, with fluctuations that defy stillness. This is the paradox at the core of modern physics. The closer we look at nothing, the more something we find. According to quantum mechanics, every point in space is filled with fields, invisible quantities that permeate the universe. Each field can vibrate, and those vibrations manifest as particles. Even when there are no particles present, the fields cannot be perfectly at rest. The uncertainty principle forbids it. There must always be tiny fluctuations of energy, constantly appearing and vanishing in pairs of opposites, particles and antiparticles born together, annihilating each other almost instantly. These ephemeral flashes of existence are called virtual particles, and they fill every cubic centimeter of space with restless potential. The energy associated with these fluctuations is known as vacuum energy, and it may be the very source of the dark energy that drives cosmic expansion. In general relativity, energy and mass both influence the curvature of space-time. If the vacuum has energy, then even empty space can exert pressure, a negative pressure that pushes the universe apart. The cosmological constant introduced by Einstein can be interpreted as precisely this kind of energy, an intrinsic property of the vacuum that remains unchanged as the universe expands. In this view, the accelerating growth of space is not powered by something within space, but by space itself. The connection between vacuum energy and cosmic acceleration was strengthened by quantum field theory in the 20th century. The equations predict that each field contributes to the total energy of the vacuum, even in its lowest state. But when physicists attempted to calculate this value, they encountered one of the greatest mismatches in all of science. The predicted vacuum energy from quantum theory is roughly 10 to the power of 120 times greater than what cosmological observations suggest. No other discrepancy in physics is so vast. The reason for this difference remains one of the most profound mysteries in the study of the universe. Despite this unsolved problem, the effects of vacuum energy are not purely theoretical. They have measurable consequences. The Casimir effect, for instance, demonstrates how the energy of the vacuum can exert force. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a tiny attraction due to the difference in virtual particle activity between the inside and outside regions. This phenomenon, first measured in 1948, is direct evidence that empty space has measurable physical properties. The same principle operates on the grandest scales. As space expands, the energy of the vacuum remains constant per unit volume. This means that as the universe grows, the total amount of vacuum energy increases. Unlike matter, which becomes diluted, or radiation, which weakens, vacuum energy does not diminish. It is this strange property that allows the expansion of the universe to accelerate rather than slow down. The more space there is, the more energy it contains, and the faster it grows, a feedback loop without end. This acceleration has another remarkable effect. Just as a black hole has an event horizon from which nothing can escape, an accelerating universe possesses a cosmological horizon. Observers within such a universe perceive a faint thermal radiation emitted by that horizon, a phenomenon first described by Gibbons and Hawking in 1977. This Gibbons-Hawking radiation is the cosmic equivalent of Hawking radiation from black holes, arising from quantum effects at the boundary between observable and unobservable regions. It means that even in the far future, when galaxies have vanished beyond sight, the universe will still glow faintly with this horizon radiation, a delicate whisper of quantum heat produced by the expansion of space-time itself. The interplay between quantum mechanics and general relativity revealed by this effect hints at a deeper connection between the very small and the very large. The vacuum that governs subatomic fluctuations also dictates the fate of the cosmos. In one sense, the universe began as a quantum fluctuation, a surge of vacuum energy that inflated into all we see. And in another, it will end as a vacuum once more, its energy stretched across infinity. Beginning and end are not opposites, but reflections of the same principle, the endless capacity of nothingness to create. Thus, even in the quiet of heat death, the vacuum will remain restless. It will continue to produce momentary flashes of existence, ripples of uncertainty, that ensure the cosmos never truly reaches zero. Space will be dark, but not inert, cold, but not dead. The last vestige of the universe's vitality will be this trembling of the void, the ceaseless, quantum heartbeat of eternity. At the smallest scales imaginable, where distances are measured in billionths of a trillionth of a centimeter, the universe no longer behaves like a smooth fabric. It flickers, fluctuates, and swirls with energy. Even when all matter and light have vanished, quantum fields continue to hum beneath the silence. These invisible fields are the foundation of everything, not empty containers waiting to be filled, but dynamic entities that define what nothing really means. The vacuum, far from being a simple absence, is a seething ocean of potential. According to quantum field theory, every type of particle, electrons, quarks, photons, neutrinos, corresponds to its own field. These fields permeate all of space, even in the complete absence of particles. When a particle appears, it is not something entering the field, but rather a local vibration of that field itself. What we perceive as matter is, in essence, a standing wave in this invisible ocean. Even when those waves settle down, the fields still fluctuate ever so slightly, prevented by the uncertainty principle from becoming perfectly still. The vacuum is therefore the ground state of the universe, calm compared to the storms of particles and radiation, but never truly at rest. These fluctuations have consequences that stretch across the universe. The same uncertainty that drives them can, in rare moments, give rise to real particles that endure briefly before annihilating each other. During the first instant of the cosmos, when inflation expanded space faster than light, these quantum fluctuations were stretched to astronomical sizes. They became the seeds of the cosmic structure we see today, the faint density variations that later grew into galaxies and clusters. Without those tiny bursts of randomness in the quantum vacuum, the universe would have remained smooth and featureless, devoid of the complexity that allowed stars, planets, and life to form. As the universe continues to expand faster than light, a similar process persists, though on a much grander and slower scale. Space that expands rapidly enough creates horizons, regions, beyond which light can never return. According to the Gibbons-Hawking effect, each such horizon has an associated temperature, meaning that the accelerating universe emits a faint thermal glow. This glow is unimaginably weak, far colder than the current cosmic microwave background. Yet, it is not zero. It represents the whisper of quantum mechanics woven into the geometry of spacetime. Physicists sometimes describe this as the universe having its own temperature, not because space itself is warm, but because observers within an accelerating cosmos experience radiation emerging from the horizon. The faster the acceleration, the higher this temperature becomes. In the early universe, during inflation, this radiation would have been intense, corresponding to a burst of heat that filled space with matter and light. In the far future, as expansion continues more gently, the horizon temperature will approach absolute zero, but it will never completely vanish. The vacuum will always radiate faintly, keeping the universe from becoming absolutely still. This interplay between quantum physics and cosmic expansion reveals something profound. Even in eternal acceleration, the universe cannot reach perfect emptiness. The vacuum energy that drives expansion also ensures that space remains active at the smallest scales. In a sense, the universe perpetually creates and destroys itself. On large scales, it expands and cools. On small scales, it trembles with ephemeral creation. The balance between these processes defines the true eternity of the cosmos. Not a static eternity, but one sustained by motion too subtle to see. The enormous mismatch between quantum predictions and observed vacuum energy remains one of the deepest puzzles in science. If the quantum fields truly contained as much energy as our equations suggest, the universe would have torn itself apart instantly after the Big Bang. Something must cancel or balance that energy almost perfectly, leaving behind only the tiny fraction we observe as dark energy today. Some physicists suspect that new physics, perhaps a symmetry not yet discovered, prevents the vacuum's full power from manifesting. Others suggest that our understanding of gravity itself must change when applied to the quantum realm. Whatever the solution, the mystery binds together the two great pillars of modern physics, quantum mechanics and general relativity, and hints at the theory that will one day unite them. The vacuum, the very fabric of existence, may hold the key. It is both the origin and the destiny of the universe, the stage upon which creation and expansion unfold. To think of the expanding vacuum is to glimpse a deeper order beneath apparent emptiness. It tells us that the cosmos will never truly stop breathing. Even when every star has faded and every galaxy has drifted beyond reach, the vacuum will still shimmer with energy, ensuring that the universe is never frozen, only whispering at lower and lower tones. Expansion faster than light forever does not mean death. It means the continuation of a process that has no beginning and no end. The cosmos, even in silence, will always hum with the faint vibration of possibility. Even in the universe's farthest and quietest epoch, when every atom of matter has decayed and every photon has stretched beyond comprehension, the quantum vacuum will continue its eternal dance. To human perception, such a cosmos would appear perfectly still, a boundless darkness where no light, sound, or motion could ever exist again. Yet beneath that silence lies the most delicate rhythm in nature, the constant vibration of quantum fields that never cease to fluctuate. It is within these infinitesimal ripples that the universe sustains its faint pulse of being. This ceaseless activity of the vacuum may seem abstract, but its effects are real. Quantum fluctuations are not merely theoretical ghosts. They are measurable phenomena that shape the universe at every level. They underlie the stability of atoms, influence the formation of galaxies, and define the geometry of space-time itself. In the early universe, they seeded the cosmic web. In the far future, they will persist as the last trace of motion in an otherwise motionless void. Every particle that ever existed, every flash of light that ever crossed space, can trace its lineage back to the unpredictable fluctuations of the quantum fields that fill all existence. The idea that nothing can never truly be nothing is one of the great revolutions of modern thought. Before the rise of quantum theory, emptiness was imagined as an absence, a stage without actors. Now, we know that emptiness is a state of potential, a restless field where energy continuously ebbs and flows. The vacuum does not wait for matter, it gives birth to it. It is both the womb and the echo of creation. Even as the universe cools and expands without end, the vacuum ensures that there is always the faint possibility of renewal an uncertainty that keeps the cosmos from absolute stillness. This principle connects directly to the mystery of cosmic inflation, the rapid, faster-than-light expansion that occurred in the universe's first fraction of a second. Many physicists believe inflation itself was driven by vacuum energy, an enormous, temporary surge of potential within a quantum field that briefly filled the universe with repulsive pressure. When that energy decayed, it released a flood of radiation and particles, giving birth to everything that followed. If this is true, then the same quantum restlessness that fills the vacuum today once ignited the Big Bang itself. The beginning of time was, in essence, the awakening of the vacuum. In an eternally expanding cosmos, the same process could, at least in principle, happen again. Quantum mechanics allows for spontaneous fluctuations large enough to create new regions of space with different physical conditions. Most of these would vanish instantly, collapsing back into the vacuum, but a rare few might expand, instead forming bubbles of new universes, each governed by its own laws and constants. In this way, expansion faster than light forever could become a kind of cosmic generator, endlessly producing new realities from the fluctuations of the vacuum. This concept, though speculative, emerges naturally from the mathematics of quantum field theory combined with general relativity. It suggests that the death of one universe could be the birth of another, that the dark silence of our cosmos might one day ignite again, somewhere far beyond our horizon. In such a picture, the universe does not end, it regenerates. The same vacuum energy that now fuels the acceleration of space might, in the deepest future, become the seed of fresh creation. Even if no new universes ever arise, the vacuum ensures that motion, however faint, continues. Quantum fields can never be perfectly uniform. There will always be fluctuations, deviations so small they might never lead to matter or light, but which nonetheless ensure that total stillness remains impossible. In the language of physics, the vacuum is metastable, poised between calm and eruption, always balanced on the edge of transformation. This balance, this eternal readiness, may be the true definition of existence itself. In this sense, the expanding vacuum represents not emptiness, but continuity. It carries within it the memory of every process that ever occurred, the vibration of every atom, the echo of every photon, the geometry of every gravitational wave. Even as entropy reaches its maximum and the universe fades into uniformity, the vacuum retains the information of what has been. It is the invisible archive of the cosmos, storing the imprints of creation in patterns too subtle for any observer to decode. Thus, the end of the visible universe is not the end of physics. Beneath the darkness, quantum fields continue to write their equations in silence. They will persist for as long as space-time itself exists, ensuring that the fabric of reality never stops shifting, never stops dreaming. Expansion faster than light forever does not erase the universe. It transforms it into something softer, more fundamental, a boundless field of potential, humming at the edge of nothingness. And so, when all else is gone, when the last trace of light has stretched beyond any horizon, the vacuum will remain restless, uncertain, and alive. It will be the eternal whisper beneath the silence, the quiet persistence of possibility. This, perhaps, is the final truth of the universe, that even in its emptiest form, it never truly ends. It endures as the pure essence of change itself, expanding faster than light, not into destruction, but into the infinite possibility of becoming. The story of expansion faster than light does not end with the early universe. According to modern cosmology, it may never have stopped at all. The same process that caused the Big Bang inflation might still be happening in distant, unreachable regions of space. This idea, called eternal inflation, suggests that our universe is not the whole of existence, but one small bubble in an infinite cosmic sea. Space itself, restless and unbounded, could still be spawning new universes, even as ours drifts into the dark. The foundation of this concept lies in the physics of inflation, first proposed by Alan Guth in 1980. Inflation describes how, in the tiniest fraction of a second after the Big Bang, space expanded exponentially faster than light, yet without breaking relativity. It was not matter racing outward, but space itself stretching. The same field of energy that powered that expansion may still exist today, decaying in some regions, while persisting in others. Wherever it continues, space inflates eternally, birthing new pockets of reality, each isolated, each self-contained, each a universe unto itself. In this vision, creation is not a single event, but a perpetual process. Every Big Bang becomes a local incident, one spark among countless others in an infinite expanse. Our observable universe, vast as it seems, could be only one small region in a boundless multiverse, a single bubble, floating amid an endless foam of others. Each bubble may contain its own version of physics, its own laws, perhaps even its own dimensions of space and time. Some may collapse instantly. Others may evolve like ours, forming galaxies, stars, and life. The multiverse, if real, is not a repetition of sameness, but a vast orchestra of variety. This idea does not come from fantasy, but from the mathematics of quantum fields. Inflation is driven by a field with enormous energy, and quantum fluctuations cause that energy to rise and fall unpredictably. In some patches, the energy drops, ending inflation and releasing heat. This creates a universe like ours. In other patches, the energy rises again, causing inflation to continue. The result is a self-replicating cosmos, where new universes form faster than old ones can cool. Once inflation begins, it never fully stops. Somewhere, always, new universes are being born. But as compelling as this vision is, science approaches it with care. The multiverse is an elegant solution to many puzzles, such as why the laws of physics appear fine-tuned for life, yet it remains beyond direct verification. The regions where eternal inflation occurs lie forever beyond our cosmic horizon. Space between universes expands faster than light, meaning no signal or particle can ever cross from one bubble to another. Even if countless universes exist, we may never detect them. This makes eternal inflation one of the most extraordinary ideas that science has proposed, and one of the most difficult to confirm. Still, hints of its possibility remain encoded in our own universe. The pattern of temperature fluctuations in the cosmic microwave background may hold subtle imprints of the inflationary field that once drove our expansion. Observations of these patterns by the Planck and WMAP missions align beautifully with inflation's predictions. Yet, so far, they tell us only about our own bubble, not what lies beyond. The edges of the multiverse, if they exist, remain hidden by the relentless speed of expansion. Physicists like Andrei Linde and Alexander Vilenkin have described eternal inflation not as a theory of beginnings, but as a theory of eternal becoming. It redefines creation itself not as a moment, but as a process without end. Every second, somewhere beyond the reach of light, new regions of space-time begin expanding, carrying within them the potential for galaxies, life, and consciousness. The multiverse, if it exists, is not a chaotic sprawl, but a natural consequence of the laws we already know: quantum mechanics and general relativity in harmony, playing out on an infinite stage. Yet the elegance of the idea comes with humility. We must distinguish what can be tested from what can only be imagined through mathematics. Eternal inflation may explain why the universe looks as it does, but until we find evidence of other bubbles, a gravitational imprint, a cosmic collision, or a measurable deviation, it remains a hypothesis, not a conclusion. Science advances not by faith, but by what can be observed. Still, this vision expands our sense of possibility. It tells us that the universe may not be singular, that creation is not confined to one event, and that eternity itself could be structured, active, and alive. Each universe, isolated by its horizon, is part of a larger whole, a cosmic network of infinite origins. If that is true, then the Big Bang was not the beginning of everything, but the beginning of our everything. In such a multiverse, every conceivable reality finds a home. Some universes may exist only for an instant. Others may last forever. Some may never form stars. Others may teem with light. Each one, born from quantum fluctuation, expands faster than light, becoming unreachable even as it begins. And this process, governed by the same physics that shaped our cosmos, has no end. Eternal inflation transforms the question of why does the universe exist into something even deeper. How could it not? The laws of physics themselves seem to favor creation over stillness, motion over rest, becoming over being. The universe, it seems, is not content to exist once. It exists endlessly, in every possible way it can. Perhaps this is the true face of infinity, not empty space, but infinite creation. Each universe a note, each expansion a breath, each horizon a boundary that hides another beyond it. The multiverse, if real, is the cosmos thinking in plurality, an endless symphony of beginnings playing out across eternal time. And within one small bubble, orbiting an ordinary star, consciousness arose and wondered what it all meant. If the universe continues to expand faster than light forever, perhaps the question of endings is misplaced. There are no endings in an infinite process, only transitions. Somewhere beyond the edges of our perception, new universes may already be forming. Space continues to breathe, and the act of creation continues. The multiverse, silent but ceaseless, is the universe's answer to its own impermanence. Even if we never see beyond our own horizon, the idea remains profound, that existence itself might be infinite in scope, that creation might be the universe's only true constant. Whether or not we can prove it, eternal inflation reminds us that the cosmos is far greater than our vision, and that beyond every silence lies another beginning. The stars we see tonight are not eternal companions, but temporary beacons in an expanding universe. Their light, though ancient, still manages to reach us across billions of years, but not forever. The more the universe grows, the less of itself it will reveal. Galaxies, once connected by the faint threads of gravity, are drifting apart faster than light, carried by the accelerating expansion of space. In time, most of them will vanish beyond our cosmic horizon, their light stretched into invisibility. For the observers who come after us, the night sky will not resemble ours at all. It will be almost empty. This transformation is already in motion. Astronomers today, using the James Webb Space Telescope, can see back nearly to the dawn of galaxies. They trace the history of light to when the universe was only a few 100 million years old. But there is a limit to how far the past can be seen, and that boundary grows closer each second. Every galaxy that crosses the event horizon takes with it an entire chapter of the universe's story. In the far future, when only the local group of galaxies remains gravitationally bound, all others will have receded faster than light, disappearing forever. In that distant epoch, the descendants of the Milky Way and Andromeda will have merged into a single massive galaxy, Milkomeda. Its quiet stars will shine against a backdrop of perfect black. No trace of the cosmic microwave background will remain. The radiation that once whispered of the Big Bang will have stretched to wavelengths longer than galaxies themselves, undetectable by any instrument. Future astronomers, even with unimaginable technology, would see no evidence of cosmic expansion, no hint of a universe beyond their own galaxy. To them, the cosmos would seem static, eternal, and alone. This is not a limitation of intelligence or science, but of nature. The accelerating expansion sets a boundary beyond which no information can ever pass. Space itself stretches faster than light, sealing off distant regions from contact. No telescope, no signal, no experiment could reach beyond that horizon. The universe will remain vast, but invisible. The more it grows, the more it hides. For us, living in this brief age when the universe is still luminous, this knowledge carries profound weight. We inhabit a unique era, one when galaxies still fill the sky, when the afterglow of the Big Bang still hums across space, when cosmic structure can still be mapped and measured. We are witnesses to a fleeting moment of cosmic transparency. In another 100 billion years, all this evidence will have vanished, leaving behind a sky so quiet that its true history would seem impossible. Yet even as the light fades, the laws remain. The universe's silence is not a void, but a fulfillment of those same principles that allowed us to see it in the first place. The equations of general relativity and quantum mechanics will still govern its behavior. Expansion will continue, unstoppable and perfect in its simplicity. The cosmos does not end when it becomes invisible, it merely passes beyond our ability to perceive it. There is something poetic in this inevitable darkness. The universe began in brilliance, then cooled into complexity, and will end in calm. The future sky will no longer speak through light, but through geometry, through the steady expansion of space itself. What will remain is not chaos, but order, not a violent end, but a serene continuation. When the sky goes dark, it will not be the death of the universe. It will be its final act of stillness. For now, we are the observers standing at the edge of knowledge. The photons that reach our telescopes are the last messages from a cosmos that is already receding beyond communication. Every galaxy we study is a farewell across time. Every beam of light, a relic from a world that may no longer exist. To look upward is to look backward and to realize that we are witnessing the universe while it can still be seen. When that vision ends, what remains will be understanding. The cosmos will no longer be visible, but its truth will persist in the laws we have uncovered, the quiet geometry of expansion, the rhythm of energy and time. Even when observation is no longer possible, knowledge will remain written into the fabric of reality. The universe will still be expanding, still evolving, still humming with the silent persistence of existence. When the sky finally goes dark, it will not mean that the universe has stopped. It will mean only that we have looked as far as light will allow. To speak of the universe's end is to misunderstand its nature. There will be no explosion, no collapse, no final curtain, only motion that never stops. The universe is not something that exists in time. It is time, stretched endlessly by the expansion of space. Every galaxy, every particle, every field is part of this unfolding continuum, moving outward in an infinite rhythm. When we ask what lies beyond forever, the answer is simple: more of the same, more space, more time, more becoming. The physics is clear. Dark energy, the mysterious force driving acceleration, shows no sign of weakening. Its pressure remains constant, causing the expansion of the universe to double again and again. Each doubling pushes galaxies farther apart until their light can no longer bridge the gap. The process does not pause. It accelerates. One day, even the faint glow of our local galaxy will be the only remnant of a cosmos once filled with light. Space will continue to grow, faster than light, an eternal motion written into its geometry. But eternity is not emptiness. Even in the farthest future, the vacuum will tremble with quantum energy. Virtual particles will flicker in and out of existence, a whisper of the same uncertainty that once gave birth to the universe itself. The expansion may never cease, but neither will the subtle rhythm of fluctuation that keeps the cosmos alive. Time will stretch on, carrying these ripples across an ever-widening ocean of space-time. The universe will not rest. It will only grow quieter. Scientists like Sean Carroll and Katie Mack describe this as a continuum without conclusion. It is not the death of the cosmos, but its evolution into simplicity, a final balance between expansion and stillness. The galaxies will fade, but the laws will remain. Entropy will reach its maximum, and yet, beneath the stillness, the vacuum will continue to breathe with quantum possibility. The universe will never reach true zero. It will remain infinite and eternal in the gentle hum of creation's residue. This vision is humbling. It reminds us that we exist during the briefest flicker of cosmic brightness, the short era when matter still forms, when light still travels freely, when the universe can still see itself. One day, that awareness will vanish, but the act of knowing will have happened. The cosmos, through us, has already witnessed its own unfolding, and that is its immortality. If the expansion faster than light continues forever, then eternity is not an endpoint, but a state of motion. The universe does not move towards silence. It is the silence becoming. Its destiny is not to vanish, but to endure, to stretch endlessly, to cool, to balance, to exist. In the farthest future, when no light remains, the laws of physics will still hum softly through the vacuum. Space will still be expanding. The continuum will still flow. And perhaps that is the most profound truth of all. The universe never ends because it was never designed to. It is not a circle, not a line, but an ever-widening wave. From the first instant of inflation to the last whisper of quantum vibration, it follows one rule to continue. Existence itself is its only purpose. The forever universe is not a destination. It is the motion of being, faster than light, beyond measure, eternal in its unfolding. Even when nothing moves, the act of expansion remains. The cosmos will go on quiet, complete, and infinite. Forever is not somewhere it will arrive. Forever is what it has always been. In the end, the universe does not vanish into darkness. It simply exhales. The same space that once blazed with stars now drifts outward in silence, carrying the memory of everything that ever was. What began as a flash of light has become an ocean of stillness, expanding faster than light, yet never beyond its own law. We made of atoms forged in dying suns were given a brief moment to look back, to see the cosmos, while it could still see itself. That moment will pass, but its meaning will not. For as long as space continues to unfold, as long as time continues to move, the universe will whisper its only truth, that existence itself is eternal motion, the quiet breath of forever.